I'm John Elder, and I'm doing a series on the deadly dozen data science mistakes, the top 12 ways to really mess up with analytics. Today, we're going to focus on mistake number 4. It's a mistake to aim at the wrong target. And I'm going to talk about targets at 3 different levels: the business, the project, and the model. How do you pick a project in the first place? That's the business problem. Then how do you aim that project at something you really want? And then how do you make the model get there by giving it the right criteria of merit? So number 1, you want to assess, first of all, the situation. You're in a target-rich environment. You're surrounded by opportunities, and it's very important to have success right from the beginning. Many people try to do too much with that first project, and it can get very indeterminate results. Because data science is a change management problem, you have to implement a new way of doing things. There's a lot of hidden resistance. So it's best to do a project that's going to get you on base, that's going to solve the problem, have a low barrier to being implemented, be a success, and gain allies and momentum. So when you want to assess the projects, each of these dots is a project. When I've given a different color to the different divisions of the organization, ideally you would choose one that has high return on investment and low relative costs. And the cost has a lot of factors we talk about in the blog and how to assess, what these costs are. So you would want something in this lower right quadrant. And I might choose, say, these 3 projects as having the best likelihood of an early success, which is so important for gaining momentum. So that's at the highest level. The next highest level is when you're choosing the goal of the project. Do you want accuracy? Do you want high returns? Do you want low cost? What is it you're actually looking for? And there I make a point that many of the default metrics that are used in data science are actually not really great metrics. They're good metrics, but they're not great. And if you really want to get the extra return from a project, it's best to customize the metric to the problem. Let's look at an example of stock prediction. You start out with a stock that's at $10 now, and your model says it's going to be 11. Looking at all this historical data, looking at the trends, everything that you can pour into the model, it predicts 11, a gain of 10%. That's really exciting. Now, there's a couple of scenarios I want to look at. The first one, it instead drops 10% to 9. And the other scenario, B, it goes up quite a bit more to 14. Now, the model, let's look at it from its perspective. After it's predicted 11, and it's going to judge itself by how close it gets. If it goes down to 9, that's an error of 2 and an error squared of 4. If it instead went up to 14, the squared error would be more than double. So you could think of it as the model would be happier, it would be less pain for it to go down than for it to go up even more. So this scenario is more pleasing to the model, if you will, but it's not more pleasing to us. Like, what happened when you thought it was 10, it's going to go to 11, is you probably bought it. And so you get this positive surprise. You really love the green scenario and not the red scenario, which is not the way the model feels about it. So your metric isn't quite right. And if you're going to make advances on really hard problems, getting that metric right is really a great example. So this actually points to the middle scale problem, which is you're not really aiming for the right thing. You don't really need to predict prices. You want to evaluate a strategy's decisions and how much that either makes you or loses you. So that should be your goal rather than actually predicting prices. Predicting the prices is useful, but it's not the closest goal to what you're looking for. And so I also talk about percent correct. Percent correct in classification is often used as the default, but that's only the right one to use if all errors have equal weight. If a false alarm and a false dismissal are equally important. But we know that if it's a fire, a false alarm is annoying, a false dismissal is disastrous. Or in something more prosaic like credit scoring, you need about 7 good customers to pay for 1 bad defaulting customer. So there's a big imbalance typically in the different costs, and percent correct is not the appropriate metric. You want to look at the overall expected cost. Likewise, when you're building models during classification and you're trying to figure out how deep to go in the model and where your best trade-off is and which model is better than another. This is the picture of one model's performance over a spectrum of different thresholds. As the model ranks the cases, your most important, most vital ones here, this we're looking at, say, home equity loans and whether they'll be paid back or not. And so you want to put the defaulters, you want the model to rank the defaulters way up at this end, and then you judge the model by how well it catches them as you go through it. The expected value for a random model would be that if you go halfway deep into your deck of possibilities, you're going to get about half the fraud. That's this red line. The perfect performance is shown by this green line. The model's performance is actually very good. It starts out nearly perfect and deviates from that, but it'll always end up being that if you go all the way through the data, you'll capture all the fraud. Ideally, you would capture it as early as possible. So the area under this blue curve, AUC, area under the curve, is the metric that is used typically to judge a model prior to your having chosen the threshold at which you're going to cut off good versus bad. What's the overall quality of the model? But that metric is mathematically incoherent, and it's not what you want at all, because what you really want is to look at the business problem and see what the cost, the relative costs of a false alarm versus a false dismissal, and that will tell you what the threshold should be and where on the model, where on this peak you want to maximize. So looking at the business costs instead of some mathematical default formula is really the best way to do it. So the point I want to make is it can be extremely valuable to be able to customize the metric to the problem. Now, the difficulty with that is you leave the beautiful quickness of squared error. Squared error is infinitely fast in regression, and it's used in almost every modeling technique. And it's correlated with goodness, but it's not as good as you can do. It's very worthwhile to have some kind of global optimization method so that you can set an arbitrary metric closer to your true business problem and then search over the possible parameter values that will optimize that and see how well it compares to the default methods. Uh, a global optimization method is a very complex topic, but you could do something as simple as a random search. Just randomly setting the parameters. If you could do this, and typically with computers, you can do this pretty fast, randomly setting the parameters and evaluating the thing and see how well that does compared to the standard methods. I highly recommend it.